Hello and welcome to Lab 1. My name is Yu Gu and I will be walking you through the important steps of this lab. Let's go over the components you will need for the Lab 1 pre-lab. You will need 2 paper clips, a standard paper cup, a D-size battery, about a meter of armature wire, which is copper wire, 1 bar magnet, piece of sandpaper, a pair of wire cutters, a 9-volt battery, and of course a battery strap. Now you are all set. Begin by placing the paper cup upside down and squeezing the magnet between the ledges. This should hold the magnet tightly. Now, bend the paper clips as shown. These will provide both support for the rotor as well as electrical contacts for the battery. Insert the paper clips between the ledge and the side of the magnet as shown. Do the same for both. You are done with the first part of the assembly. To make the rotor, you will need the D-sized battery. Take the armature wire and wind it around the battery about 10 to 15 times. Secure the armature loops with the remaining wire. You will need to strip the ends of the rotor before placing it on the paper clips to achieve an electrical connection. The easiest way to do this is to place the wire on a table and sand away the dark red insulation. On one side, the wire should be stripped entirely. The other side will be the commutator, and you should only strip a 90 to 180 degree arc. Think about how current flows through the wire and the forces acting on the rotor. This will tell you which part of the wire should be stripped. Now attach a small flag to one end of the rotor, which will be used to measure its rotational speed. Finally, attach the battery using the battery straps to the ends of the two paper clips. Now place the rotor. If everything's done correctly, your motor should spin. Use the photoresistor setup shown in your lab handout to measure the frequency of your motor. Position the flag such that it's right between the photoresistor and your laser pointer. A periodic waveform should appear on the oscilloscope. Use the Run Stop button to capture this waveform and measure the frequency. For this part of the lab, you will need a geared DC motor, as well as some banana jacks. In addition, you will need a power supply which operates in constant current and constant voltage modes. Connect the geared motor to a constant voltage input. Because the voltage sets the rotational speed, it should be nearly impossible to stop the shaft with your hand. Notice the current will increase as the resistance is increased. Now put the power supply in constant current mode. When the motor constant is unchanging, current will set the torque of the motor. It should be easy for you to apply an equal torque in the opposite direction. In this part of the lab, you will be characterizing a specially built DC motor. Let's start with a wound field motor. You will need a constant 5-volt power supply and a variable power supply. Start by connecting the two solenoids in series. Connect the multimeter in series so it will be used as an ammeter before connecting everything to the power supply. Use the 5-volt power supply to power the rotor. Adjust the variable power supply so the current in the solenoids is about 0.5 amps. Now you will take a series of steps to find the optimal motor constant K for the wound field motor. The first step is finding the motor constant of the permanent magnet motor, or kpm. After you have verified the wound field motor is working, turn off the current in the solenoids. In this case, the power supply displays the current reading, so we no longer need the multimeter. The current through the solenoids should be constant at 0.5 amps. Connect the rotor now to a variable voltage output. Set the multimeter in voltage mode and use it to measure the back EMF from the permanent magnet motor. If we can turn the motor shaft at a known rotational speed and measure the back EMF, kpm is found by taking the ratio. You will collect this data for 4 different rotor voltages. Use the same photoresistor setup described in Lab 1 to measure the rotational frequency. It is convenient to use the 5-volt constant voltage output to bias the circuit. Set up the oscilloscope to take the voltage across the photoresistor. Generate the signal using a laser pointer and measure both the frequency and back EMF for wound field rotor voltages 4, 5, 6, and 7. Now you will find the constant C, which relates the wound field motor constant to the current in the solenoids, also known as I stator. The 5-volt constant voltage supply should now be connected to the PM motor. The multimeter should now be used to measure the back EMF from the rotor terminals of the wound field motor. First measure the rotational speed with no current applied to the stators. Then turn on the current to the solenoids and measure the back EMF and rotational speed for currents ranging from 0.3 to 0.9 amps. The particular range of current may be different according to your motor. Note that to observe the periodic waveform on the oscilloscope, you may need to adjust the timescale. When you're done, calculate the motor constant of the wound field motor from the back EMF and plot K wound field as a function of I stator. Determine C from the slope of the line. Now you will find the optimal wound field motor constant, the one which maximizes its rotational velocity. Connect the 5-volt power supply again to the rotor of the wound field motor and use a multimeter to measure the back EMF of the PM motor. Now you will change the wound field motor constant by changing I stator. You can observe the result either by measuring the back EMF and finding the corresponding rotational speed, or measuring the rotational speed directly. From I stator, you can calculate the value of the motor constant using the data acquired previously. When you're finished with collecting data, plot rotational speed versus the motor constant. You should see an optimal point.